Okay, so zooming in on points and save percentage, are the differences over the years statistically significant? So for this, I did a one sample t-test to see if the value, which essentially for the t-test we would say is our sample mean or our example mean, is that actually our mean. So in 2018, the average points of the top scorers was 90.35 points. So we're going to run a t-test against our points frame to see if that's actually a significant change. So since our p-value here is 0.4429, we can say that um, it's actually not statistically significant. So the true mean falls within our 95% confidence interval, and so does our test value, meaning that it's more than likely that this is a run-of-the-mill season over the past, like compared to the past 30 years. The last season was a run-of-the-mill season as far as statistical performance goes in points. So we can see that our mean of points over the past 30 years of the average scoring leader is 88 points, with a standard deviation of 13.14 points. So it's not a statistically significant year in points, but there's this conception that points have been steadily increasing. So that's kind of interesting, I think, to look at, because the NHL has been very vocal about their uh, interest in increasing scoring, but there's also been a lot of changes to what teams are allowed to do defensively that's actually sort of curbed that. So let's have a look at save percentage. So save percentage is very interesting. So last year's average save percentage was 0.9276, which, just as a some anecdotal thinking, is a very high save percentage. So if we do the same test we did before, we see that our p-value, or our probability of finding stronger evidence against the null hypothesis, is 0.9 or 9.339 times 10 to the negative 6, which at a confidence level, or at a significance level of 0.05, we can say the difference is actually significant in this case. So last year, 2018, was actually a statistically significant year as far as save percentage goes. Um, as we can see, our mean of save percentages over the past 30 years is 0.9186. Now, from an outside perspective, these don't really seem like very far off percentages, but when you consider the difference in the top 20 of save percentage is so small that this is actually very statistically significant, especially when you look at our standard deviation, which is only about 0.8%. So that means that a 0.9276 save percentage is actually quite statistically significant. So that was very interesting for me to figure out. Now, obviously, if you are sort of up to date on your history with the NHL, you'd kind of understand why this is the case. So even though the officiating has become more hard on penalties and giving more opportunities for teams to score on the power play, it's also been, and increasing net size and things like that over the past 30 years. It's also been good to goalies, because goalies have increased pad size steadily up until the last few years, uh, and that I believe personally contributes largely to the increase in save percentage. Now again, the NHL's come out and said that they want to sort of curb that as well. So we'll see what happens in the next few years, if those kind of almost flip flop. So points start to increase massively compared to save percentage either changing or like decreasing or staying the same. I also contribute this more to goalies being a lot more athletic than they used to be. Goalies are now very tall, very strong, prototypical guys that could probably play other positions on the ice, as compared to previously, where goalies were more the smaller person, just agile, not so athletic, not as traditionally athletic as was kind of the norm. So I think those kind of things contribute to the increase in save percentage, statistically significant increase in save percentage compared to points where, points there's only so many points you can score in a year, and the NHL does all it can to score more. But when everybody on the other side of the ice, on the defensive side of the ice, is more athletic than they used to be, the increase isn't actually as significant as it would seem. So now what will be interesting is to try to predict future performance based on the data we have. Now this would be trying to predict the average scoring leader based on the past 30 years data of average scoring leaders, or average points leaders, or average assist leaders, goals leaders. Again, we're going to focus on points and save percentage here, just sort of to keep that going. Again, mini project, so this is, again, a taste of what you could do. So to do that, I created a linear regression for both points and save percentage, and did a bit of variable selection just manually. Again, this was for more of an exercise, so I didn't run any optimized selection procedures on here, because it's more of a look at the quick analysis and sort of have a discussion about how you could further this in the future. So I started off with a full linear model of points, which is this here. So that includes plus minus penalty minutes, shooting percentage, minutes, plus minus, and then a bunch of interaction terms. Interaction terms are when you multiply one term by the other in a linear model. So when you run this, it essentially creates a linear regression that gives you an equation to come out with points based on all the other factors. So now if we go summary of that model, it'll actually give us each of the predictor variables. So since this is a full model, we actually don't look at the p-value for the first order terms. We're first going to look at the p-values for the interaction terms, and I always set a preliminary significance level of 0.05, so that's what I used here. And as we can see, plus minus times shooting percentage is a significant factor. So now we rebuild the model with that in mind. So points predictor with the interaction model in here. So we can actually see our full model has a R-squared value of 0.8674. I then will go and run just the predictors without any interaction terms, and we'll see what that looks like. So these four predictors, plus minus penalty minutes, shooting percentage, and minutes, actually turn out to be important. However, penalty minutes and minutes were actually not quite that important, so I removed those from the model, which gave us actually a lower R-squared value. And now I combine those things into our interaction term here, which gives us kind of the model that I would go with, 0.8303, which I believe is a lower R-squared than the full model. Yeah, it's a lower R-squared than the full model. However, for this analysis, I believe it's better because we have less variables, and our variability is going to be lower in this. So we chose our points prediction interaction term model here. Now, moving on to save percentage, I ran, this is the full model for save percentage. I didn't run the full interaction model because it was enormous. So I just ran this, and I picked the variables that had a lower p-value. So games played goalie, which is just the games played for that season for the goalie, the average saves, and average goals against average. So just this full model gave us already a R-squared of 0.9725, which is pretty interesting. But now, obviously, when you have every statistic that made up a goalie season, if the data is remotely normally distributed, you're going to have a pretty good R squared value, adjusted R squared when you look at predicting. So I kind of wanted to strip it down and see what we could get to uh, based on things that you might be able to predict a little bit easier than for instance, shutouts in a season for a goalie, which is quite unpredictable. So what I did was I brought in the reduced model, which is just games played plus save percentage and goals against average, which actually gave us quite a good R squared value still. And our F statistic is significant. So I then decided to run an interaction term analysis just to see what that looked like, but actually it gave us a lower p-value, and none of our interaction terms were significant. So I kept actually just our save percentage reduced model for the rest of this analysis. Now, we need to check our assumptions. So for linear regression, there's a few assumptions that we need to check to see what exactly, like if we can actually apply linear regression to this data. So one of those is or actually, you know what? I will break this video and then we will come back on the next video. Thank you.